So we're looking at relativity here, just as a rough intro to see how it came about. First of all, when we're dealing with stuff, I always like beginning with stuff. Stuff in your everyday kind of normal frame of reference, at the same size as we are, so we're talking about size, and it moves at around about the same speed that we can easily observe. It turns out that it's fine. And all our observations and things are all a-okay when we're in this normal frame of reference. However, as soon as we start moving things a little bit faster, like speed of light kind of faster, some interesting effects start happening. And that's what this idea of relativity deals with, things moving very, very fast. Quantum physics deals with the physics of things very, very small, which are also outside this kind of normal, if you like, frame of reference. Normal being relative to us, we, as I said, our size and our speed and the things we can observe very carefully, things that are Newtonian classical mechanics. But anyway, approaching the speed of light with things, there are a few interesting observations. I'm going to start with a little bit of history to show where Einstein and special relativity, what was kind of the groundwork for that. So first of all, we had these guys, Michelson and Morley. What's the date? 1887. They performed a very clever experiment, because way back then there was this thought that space wasn't empty. They thought there was something called ether, A-E-T-H-E-R, and that was the substance of nothing, if you like. So that all the planets and stars and everything are moving through this ether and the ether was kind of a frame of reference, a fixed kind of thing. So to give you the idea of what they expected to happen in an experiment they had, they considered two boats. There's a riverbank here, and you've got two boats. One of them is travelling across and back, so it's going there and back, and the other boat is going this way and then back again. The river also has a current, and this was kind of likened to planets moving through space. So a planet moving through space is also inside this current of ether. But what you would expect for the boats in this case is that it would take longer for one boat to travel across equal distance. So if that was 20 meters and this was also 20 meters there and back, because they both have a frame of reference to the water, they'll each take different amounts of time to return. And you can go and look at your Year 12 physics to do with vectors and the classic river crossing situations to work that out. But they each are fighting against the current by different amounts because of their own individual velocity maximums and different things like that. But anyway, what was expected was when they did this, I'll tell you the other experiment. The other experiment was that they did the same thing with the light. They had a light source and they shined that there and back, and they also, at right angles, they shined another beam there and back, and they expected to see the same difference due to the movement of the ether, or the movement of the light relative to the ether, and that the light beams would have to be working against the current, if you like, the ether. But what they discovered was that there was actually no difference at all in the time that it took. So it was exactly the same amount of time for them to cover the same distance regardless. So that experiment showed them that there was no ether. Which kind of threw a spanner in the works, because previously motion of planets and stars and everything out in space, it was easy for scientists to think of it in terms of moving in a fixed frame of reference, with the stuff of the universe was fixed in place, or the ether itself. So it wasn't the case. And then along came Einstein, and whoops, Einstein has one E. Einstein, and he came up with a special theory of relativity, special relativity, and it's why I won't fit on the screen. Relativity, and he started from two assumptions or two principles to work out what would happen. So the first principle is that there is no absolute frame of reference. Okay, so no absolute frame of reference. If he always talks about trains. They always talked about trains because trains were common back then. And if you're on two trains going side by side and you're staring at each other, and both the frames, both the trains moving at the same speed in the same direction, you couldn't tell that the other one was moving. But we do have an absolute frame of reference in that case, which is the ground beside. So you could look out and see the ground as well. Well, Einstein said that there's no absolute frame of reference, so you can get rid of the ground, and then you don't know for sure if anything is moving because there's nothing to compare it to. Could be that everything else is moving. So the Earth moving through space, it could just be that the space in the whole universe is moving around the Earth. It's an equally valid frame of reference to swap it around like that. Number two, his second, I'll just move it down a little bit. His second point was that the speed of light, c, is the same, and this is a really tricky one, for any observer at all. Any observer. And you can imagine, we'll give you an example. If you had, this is from an old physics textbook, Form 7 revision by Paul Howison in New Zealand. He gives the example of two fighter planes that are flying towards each other, and if one fires, so here's one plane flying towards one, it's pointing in that direction, and the other one is also going in that direction. If they're both going 100 meters per second, and then this one of the planes fires a rocket off at 200 meters per second, then the ship number 2 here will see that this rocket coming towards him at 300 meters per second because he had the 100 and the 200. Now, what Einstein said was that if they're both going the speed of light, so instead of going 100 meters per second, they're going the speed of light, and then you fire this rocket at 200 meters per second, that rocket is not going at c plus 200. It doesn't seem to be going at c plus 200 to that second fighter pilot. So, yeah, I don't know exactly how he came up with this idea, but what this did mean was that if the speed of light is fixed, so even if this rocket is fired forward at 200 meters per second from something already moving at the speed of light, that the speed of light would still be constant. So even though it might be moving ahead of it, ahead of plane 1, it's still only moving at the speed of light maximum. And what that has the effect of doing is affecting the length of certain things, the time of certain things, and mass. So these things must change in order to keep c the same, so that it doesn't destroy the whole universe or something. But but these are the things what he was talking about, and I'll get into that in a later video. But length changes, time changes, and mass changes, and you get funny effects, sort of like the warp, going into warp on Star Trek, and you see all of those shifting colours and lengths and things. Old sci-fi movies used to show people slowing down too as they go into warp speed. But anyway, that's the first intro. We'll get into that in more detail in a subsequent video.